Welcome to the fourth session on ionic equilibria. In this, we will be dealing with the relative strength of acids and bases. Now, relative strength means there is a comparison, how far an acid is strong, how far an acid is weak, or how far a base is strong or how far it is a weak base. We are going to compare that strength. Okay. Now, the relative strength of an acid and base is considered as the extent to which it ionizes when dissolved in a solvent. How far it ionizes. Okay. If the ionization reaction is complete, that is, they are completely converted into ions, we call that acid or a base to be strong. This we have seen in the earlier session. And if ionization occurs to a very little extent, we call that acid or a base to be weak. Okay. If it is completely ionized, we call that to be a strong ones, whether it be an acid or a base. If it is only feebly ionized or very little ionized, we call that to be a weak acid or a weak base. Okay. Now, what are the factors that determine the extent of ionization of an acid or a base? Let us see the factors on it one by one. First one is influence of the solvent. In influence of solvent, we have two categories. First one is effect of proton accepting or donating nature of a solvent. Again, just remember, if proton accepting and donating nature of solvent, if we say that, we know that acids and bases, they depend on, if it is a very good acid, that donates its proton easily. Okay. If it is a very good base, it accepts a proton easily. So, donation and acceptance depends upon in what solvent we are taking that acid or a base. So, influence of the solvent is very important, and in that the first one is effect of proton accepting and donating nature of a solvent. Okay. Let us see some example. Here acetic acid is taken as solvent and I am going to add nitric acid to that acid. Okay. So, these both are acids. So, what happens is nitric acid, it likes to donate a proton, but acetic acid, that is also an acid, but actually it is a weak acid. It does not have that capability like nitric acid to donate a proton. But what happens is, being a solvent, acetic acid will be compelled to accept a proton, though it is not that liking to accept a proton. So, what happens is, an acid can act as an acid only if someone accepts its proton. If there is no one to accept a proton, the acid cannot donate a proton, and therefore, acid cannot function as an acid. Now, here that is not the case. Actually, acetic acid, being a weak acid, it can accept a proton compared to that of a nitric acid. So, what happens is, by force nitric acid gives a proton to acetic acid. So, acetic acid gets protonated. Now, what happens here is, acetic acid gets protonated with NO3 minus, that is, a nitrate ion is formed as a byproduct. Now, here if this acid has been added to water as a solvent, that is what shown in the next case. Water which is capable of accepting protons as well as donating protons, but not to that extent just like an acids. So, what happens is, nitric acid readily donates the proton to water. Okay. And what happens is, water, it gets converted into hydronium ion, H3O plus ion and nitrate ion. Now, just compare these two arrows. In the first case, the backward reaction is preferred because acetic acid actually, it is not that willing to accept a proton, but under compulsion it accepts a proton from nitric acid because nitric acid is stronger than acetic acid. Now, acetic acid has got more tendency to give out its proton rather than accepting the proton. So, I have put a longer arrow on this side. You can see that the backward reaction is more favorable than the forward reaction. But in this case, second case, when we take water as a solvent, water readily accepts the proton, and therefore the forward arrow is a larger arrow than the backward arrow, because backward reaction is not that preferred. Okay. So, when we compare these two, see, I have been taking acetic acid as a solvent as well as water as a solvent. When I took acetic acid as a solvent, nitric acid acts as a weak acid, while when I take water as a solvent, nitric acid is acting as a strong acid, readily donates its proton. So, the extent to which it donates a proton determines whether that is a stronger acid or a weaker acid. But since nitric acid in two solvents, see, you can see, depending upon the solvent, it acts sometimes, that is in the acidic solvent, and that solvent was a weak acid solvent. Okay. So, what happens? Acetic acid acts as a weak acid because that was an acidic solvent. When we took water as a neutral solvent, nitric acid acts as a strong acid. Okay. So, depending on the proton accepting and donating nature of a solvent, the strength of acid varies. See, nitric acid, in both cases we have two types, that is, in one case it is acting as a weak acid, the other case it is acting as a strong acid. Okay. When nitric acid is added to hydrogen fluoride, which acts as a solvent, what happens is, hydrogen fluoride is a very strong protonating solvent. Now, what happens is, nitric acid will not be able to donate its proton to HF. Instead, HF protonates nitric acid. So, you can see that HF protonates nitric acid, and nitric acid gets converted into H2NO3 minus. Now, here you can see the arrow, that is, you have a longer arrow in the backward direction and a shorter arrow in the forward reaction. Now, which means that H2NO3, after accepting a proton, it is very unstable. It readily gives out its proton and converts back into nitric acid. So, here, since nitric acid is accepting a proton from HF, it is acting as a base, but it does not like to keep that proton. So, it easily dissociates, and therefore, it is considered as a weak base. So, just compare nitric acid. You are having different solvents. You are having acetic acid, water and HF. In the case of acetic acid, nitric acid was a weak acid. In the case of water, it was a strong acid. But when we come to HF, you can see it acts as a weak base. Okay. Now, let us take the case of acetic acid. Again, the solvent is HF, which is a highly protonating solvent. Now, in this case, it protonates nitric acid, but surely it can protonate acetic acid too, protonates acetic acid, and here acetic acid gets protonated and fluoride ion is left back. Now, comparing these two, see, here HF was acting as a weak base, HNO3 was acting as a weak base in HF solvent, but in this case just check, acetic acid, which is an acid, weak acid in aqueous media, becomes a strong base and it gets converted into this, and therefore, you can see there is a forward arrow being a larger one and the backward arrow being a smaller one, which means that acetic acid is easily protonated. Okay, so it becomes a base. Now, consider the same acetic acid in ammonia. Here, ammonia actually it is a base and it is ready to accept a proton. Acetic acid is a weak acid actually in water and it has got a tendency to donate a proton, but ammonia when compared to water, it is ready, it is craving for a proton, and therefore, it accepts proton readily than water. Therefore, acetic acid easily donates its proton to ammonia. Okay. So, since it is easily donating it, it will be a strong acid. it gets converted into acetate ion and ammonium ion. You can see the arrow mark is larger towards the forward direction, and therefore acetic acid will be a strong acid in ammonia, because ammonia is ready to accept a proton. So, in this all these we can understand that the acidic property or basic property depends upon the proton donating or accepting character or capability of the solvent. Next is effect of polarity and dielectric constant of a solvent. See, you can see that there is dielectric constant, it is a measure of polarity of the solvent. High dielectric constant means that solvent is highly polar. Okay. So, what happens is greater the polarity and dielectric constant. So, both are same. Okay. It is a measure, dielectric constant measures the polarity of the solvent, greater is the reduction in the forces of attraction between the ions of the solute. That is a general case. Okay. Now, if that helps, that is, suppose I am having HCl. Okay. So, there is an attraction between H plus ions and Cl minus ions. If the solvent polarity or dielectric constant is greater, the attraction between these two becomes weak. Okay. So, what happens? HCl is capable of donating the H plus ions. Now, let me take another one like sodium hydroxide, Na plus and OH minus ions. Here, there is attraction between Na plus and OH minus ions. Now, if the polarity of the solvent is greater or its dielectric constant is greater, these attraction gets weakened. So, what happens? It readily ionizes to give its ions. Okay. This results in the strength of the acid or the base dissolved in it. So, if the polarity of the solvent is greater, acid becomes stronger acid. Base becomes a stronger base because it can readily donate its ions. Okay. So, polarity or dielectric constant of the solvent also determines whether an acid is a stronger or weaker one. Okay. Next is nature of substituent. Nature of the substituent, usually we consider this in organic compounds. The example we will be taking is a trichloroacetic acid. Trichloroacetic acid, everyone knows that is CH3 COOH, that is acetic acid. Acetic acid whose 3 hydrogen atoms are substituted by chlorine atom becomes trichloroacetic acid. Okay. Now, just think of this carbon attached to 3 chlorine atoms, and then comes COOH. For trichloroacetic acid to function as an acid, we have the H plus ion, that is hydrogen, to go from here as H plus ions. That is what we need. If it goes faster or readily, we can say that is a very strong acid. Now, this chlorine atom, as we all know, it is highly electronegative. So, what happens is this pulls the electrons of the carbon atom. How many chlorine atoms are there? 3 chlorine atoms, they are pulling the, and as a result this carbon pulls the electrons from this carbon, and finally what happens is this bond weakens, that is between the OH bond weakens, and since there is a deficiency of electrons are felt here, what they do is they take up the electron of hydrogen atom and let hydrogen go as a proton. So, that is what we say, that when electron withdrawing substituents, this is the electron withdrawing substituents, are present, the acidity increases. When electron withdrawing substituents are present. Okay. For example, if you take acetic acid, it does not have any electron withdrawing atoms on it, it is hydrogen atom, and therefore acetic acid will have a certain amount of acidity, but compared to acetic acid, trichloroacetic acid is more acidic. The reason is that it has electron withdrawing groups in it. Hope it is clear. Next is electron donating substituents. We will see the basicity of ammonia and amines. Ammonia, that is nitrogen atom having attached to 3 hydrogen atoms with its lone pair. Ammonia is basic, it is capable of donating its electron to someone else. Now take the case of nitrogen with one of the hydrogens substituted by CH3 group and other 2 being hydrogen atoms, and you have, this is known as methylamine. This will be, I am going to write it as dimethylamine. That is 2 of the hydrogen atoms, I am converting it into or replacing it with methyl group, and all these have electron, lone pair of electrons. The methyl groups, they are electron donating groups. CH3 groups are electron donating groups. Okay. Now, these groups, they donate electron to nitrogen. Now, what happens is when these they are pumping their electrons to nitrogen atom will not feel the severe need of this electron pair, and these electron pair will be donated easily. So, here 2 groups are present. In this case, we have one methyl group which is pumping its electron or electron donating group, one electron donating group, that is a one methyl group. While in the case of ammonia, you do not have any methyl group. So, what happens is, which will be more basic? The dimethylamine will be highly basic compared to the other 2, and next will be methylamine, and the least will be ammonia. Okay. Next is steric effect of substituents, because here I have not considered the trimethylamine, which will be dealt in the steric effect substituents. Now, when we consider the above case, we can consider the trimethylamine too, that is all the hydrogen atoms being substituted by the methyl group. Okay. Now, here the steric effect is because of the size effect, very big size. Okay. Now, methyl groups are bulk groups. They are all bulk groups, means they are larger in size, while if it is a hydrogen atom, that will be small in size. So, in the case of trimethylamine, okay, you have 3 bulk groups attached to nitrogen. Actually, it will be like this, that is nitrogen surrounded by 3 big groups. Though it has got a lone pair, none of the atom, let it be a proton or whatever it is, the molecule whichever it is comes near it, here it cannot approach near nitrogen's lone pair. If it is only approachable, you can donate. It is due to the crowded effect, and this crowded effect is known as the steric effect. Due to the steric effect of the 3 bulk methyl groups, nitrogen is not able to donate its electron pair, because due to the steric effect of the bulk groups, and therefore, trimethylamine is less basic, though it has got 3 groups which are electron pumping, but it is of no use, because none of the atoms or molecules can approach the lone pair on the nitrogen atom. Okay, and that is known as the steric effect. Next is p pi back bonding. Let us see what is it. Here we are considering two compounds, that is BF3 and BCl3. Sorry. BCl3. Now, here just check the size of these halogen atoms. F size less than that of chlorine atom. Okay, so smaller in size. When the size is smaller, what happens is BF bond will be smaller because they can come closer because the size is small. The BCl bond will be a bit far because chlorine atom has got larger size than fluorine atom. Okay, so that will be a bit far. Now, here what happens is, since boron, as I told you before, it is an electron deficient compound. It has only 6 electrons in its outer orbit, and therefore there is a deficiency of electron in boron trifluoride as well as in boron trichloride. Now, here what happens is, you just check the bond length. Okay. In the case of boron fluoride, fluorine is closer to boron, and therefore what happens, the p orbitals of fluorine atom which contains lone pair will overlap with the empty orbital, p orbital of boron. Okay, that is a filled orbital of fluorine, and that is a lone pair, not the bond pair. Lone pair of fluorine atom, p orbital, overlaps with the empty orbital of p orbital of boron, and thereby reducing the electron deficiency of boron. And that is possible only if the boron and fluorine atom are closer together. But when they are far apart, because chlorine has got a larger size, it cannot overlap like that. Okay. And when we come to bromine, it will be larger, there won't be any overlap of that sort. And this type of overlap, that is fluorine atom, the p filled orbital of p orbital of fluorine overlapping with the empty p orbital of boron, is known as p pi. It is a pi bond, therefore it is known as p pi back bonding. It is known as p pi back bonding, and therefore BF3 does not have that electron deficiency as in BCl3 or BR3 . Okay, as we go down, the size increases. So, it will be here, it is a comparison between BF3 and BCl3. BF3 will be less acidic than BCl3. The reason is, in BF3, p pi back bonding is possible because the size of fluorine is smaller and the bond length of boron and fluorine will be shorter compared to that of boron and chlorine. Okay. Next is factors such as electronegativity and charge density and hydration energy. Here we are going to check. See, here we have hydrides of nitrogen, oxygen and fluorine. What are their electronegativities? Nitrogen less than, oxygen less than fluorine. Okay. As the electronegativity increases, okay, when electronegativity, that is of the hydrides, when electronegativity increases, what happens to the acidic character? Acidic nature or character increases because HF is highly acidic. Okay. Ammonia, you can see that is basic, and water you can call that to be amphoteric. Got it? The electronegativity of the anions, just check the anions in this. All these are electronegativity is highest for fluorine and therefore that is highly acidic. Now take the case of the halogens itself, HF, HCl, HBr and HI. Now when we consider the electronegativity, it is highest for fluorine, but you can see their acidic nature. This is the acidic nature. Okay. HF has got the least acidic nature while HI got the highest one. Now why is it so? This is because the electronegativity is not the factor. Here we have to consider the charge density and hydration energy. What is charge density? When the size of the atom is small and it carries an unit negative charge, the unit negative charge will be spread in a very small area. See like this. The case of fluorine, if this is fluorine, this is small, and if it carries a fluoride ion, this is spread along this area. Now this is chlorine. Compared to fluorine, chlorine is bigger. Now what happens is, it also carries a unit chloride ion, it becomes chloride ion. What will be the charge density around it? In such a big area, a unit negative charge, so charge density will be less. Again when we go to bromine, it will be charge density will be less, and in the case of iodine, the charge density will be the least. Okay. Next is, so charge density is one of the factor, because if charge density is high, it is just like a magnet. If the negative charge is very strong, high powerful negative charge, it won't allow the proton to separate from it. Okay. When the charge density is low, proton can be easily given out. So since charge density is lower, charge density will be in the order, how will it be? Charge density is highest for fluorine, then comes chlorine, then comes bromine, and then comes iodine. I mean, you take the ions. Okay, fluoride, chloride, bromide ions, that is, actually hydrogen should go out, but the charge density on iodine will be very less, so it won't attract the H plus ions, it will let the H plus ions go. The others and all, fluorine is, it's got a highest charge density, it won't let the high H plus ion to leave from it. Okay, that is one factor. Then second factor is their hydration energy. The hydration energy is the energy released during hydration, and that will be a negative value, and the hydration energy for these ions increases as we go from fluoride to iodine. Hydration energy is also favoring that, and with those two conditions, the acidic nature of hydrogen iodide is greater, because from hydrogen iodide H plus ions are easily departed or it is donated. Besides, the charge density on iodide ion is less, it gets highly hydrated, so that iodide ion is stable and therefore highly acidic in the case of hydrogen iodide, and as we go down this side, HF is the least acidic substance. So here it depends upon electronegativity, charge density and hydration energy. Now let us see what is the resonance effect and what is its effect on acidity of phenol. Phenol is C6H5OH, and phenoxide ion, that is, when phenol loses this proton, it becomes C6H5O minus. Okay. Now let us first see the resonance structures of phenol. So phenol, the 3 double bonds, OH with its lone pairs. Okay. Now this oxygen, the lone pair of oxygen gets into resonance into the ring. See, it utilizes this lone pair to form a bond over here, and what happens is this pi bond will be shifted to this corner. So you get one resonance structure, that is pi bond is shifted to this corner. the other two bonds intact, and here there will be a double bond with oxygen lost its lone pair in making a bond over here, and it carries a positive charge. Okay. So, next one will be this electrons are utilized to form a pi bond over here. At the same time, this pi bond shifts to this corner carbon atom. That is, you will have a structure with this over here, the pi bond new created over here, and the other pi bond as such with double bond O, positive sign H. Okay. Next, this pi electrons are utilized to form a pi bond, while this pi bond shifts to this corner. So, you have the next one. Here a new bond is formed, the other electron shifted to the corner, double bond O with a positive charge, the other parts as such. Okay. Now, this electrons form a pi bond over here, and oxygen takes back its lone pair, and you will get another structure. That is, when oxygen gets back its lone pair, it does not have any charge, the lone pairs are back, okay, the double bond is gone, you have a new pi bond created over here and this. So, you have two structures, this is one keculeiform and this other keculeiform, and we have three other polar structures. In all these, you can see that the positive charge is being, that is, three of them has got polarity in which a positive charge resides on oxygen atom, or you can say that oxygen has a slight positive polarity. Okay. So, when oxygen has got a slight polarity, it is easy for the hydrogen to depart as H plus. Okay. Now, once H plus is lost, we have the phenoxide ion. The phenoxide ion, now let us see what is the case of a phenoxide ion. O, hydrogen, that is the lone electron pair got from hydrogen 1, that bond pair, and the other bond pair, and with a negative sign. Okay, this phenoxide ion, just like as in phenol, it can utilize one of its lone pair to create a bond over here and this shift to this corner. So, I will write it fast because we have been discussing it in the other way. The only difference is in this case it is a phenoxide ion. So, here we will have a minus sign, the other two bonds as such, double bond O with two lone pairs and a positive sign. Sorry, not a positive sign, there will not be any sign. It becomes neutral because that negative sign electron is being utilized here to form the double bond. Now, again next one, double bond O, two electrons. This electron pair becomes, and this shifts to the corner. So, here I will have a pi bond, here another pi bond with double bond O. Next, goes here, this to the corner, and we have double bond O with the lone pair. Okay. Next is this comes over here to form a pi bond, the lone pair is given back and you get the second structure. that is 1, 2, 3, double bond O, the electron pair has come back and there will not be double bond. That will be a single bond with a negative sign. So, these two, that is cases, this one case and this other case in which oxygen is carrying a negative sign on oxygen atom, but this has been delocalized or resonated throughout the ring, and therefore, phenoxide ion is stabilized by resonance. Okay. The other case, it was a positive charge which accumulates on the oxygen, which favors the removal of H plus, and the phenoxide ion, resulting phenoxide ion formed, you can see that it is resonance stabilized. So, this is stabilized. These two factors favor phenol to be an acid. Okay. So, resonance effect also contributes to the acidic nature of a substance. Next is leveling solvents and differentiating solvents. We have already heard about the relative strength of an acid. So, relative strength is how far or the extent to which the acid can ionize or a base can ionize in a solvent. Now, the solvent whose proton accepting characters or proton donating tendencies is in such a way, what they do is they make the ionization of acids and bases to the same extent, and therefore, they appear to be equally strong. So, certain solvents, there it can be either proton accepting or donating tendency, in which you can add acids or bases, different acids and different bases. All these acids and bases, they ionize to the same extent. Okay. So, when they ionize to the same extent means they are equally strong or equally weak, whatever we take it. So, the strength of the acids become equally strong. Such solvents are known as leveling solvents, and effect is known as leveling effect of the solvent. So, there are certain solvents like that. Now, if the strength of all acids stronger than a characteristic of cation of the solvent, this is based on the solvent concept of system, in which we say that the cations are strength are increased or anion strengths are increased. Okay, based on that, the strength of all acids stronger than the characteristic cation of the solvent would be leveled to the characteristic cation of the solvent. They are leveled. They cannot show more. They have to be leveled to the solvent cation. So, that is known as the leveling effect. In the same manner, bases stronger than the characteristic anion of the solvent will be leveled to the characteristic anion of the solvent. So, whether it is a stronger acid or a stronger base, once we add that to the solvent, what happens is, if it is an acid, its cation strength, how much it is leveled to that. Okay. And if it is a base, it is leveled to the anion of the solvent. For example, HA, let it be whatever be the acid, when added to water, it becomes H3O plus and A minus. No acid can have stronger than H3O plus in water. So, if we add any H3O3, HNO3 or any of the acids to water, every strength or the ionization of these acids are leveled. You cannot say whether nitric acid is more stronger or sulfuric acid is more stronger. All are leveled to the cation of water, that is H3O plus. Okay. Then when we come to the base, no base can be stronger than the OH ion in water. So, OH ion is, what is the basicity? The same basicity will be the strength of all the bases added to water. See, NH2 minus is a amide ion, added, let it be sodium amide or whatever it is. When added to water, it goes to OH minus and NH3. Sorry, it is NH3. Okay. So, what happens? It's all made level to the OH minus ion. But there are certain solvents where the proton donating or accepting tendency is that different acids and bases, they ionize to different extent in those solvents. So, in that solvents you can differentiate the extent of ionization of an acid or a base, or you can differentiate them like which is stronger and which is weaker. Such solvents are known as differentiating solvent. For example, if I take acetic acid as a solvent, this is a solvent, and I am adding an acid. Okay, you will have an ion CH3COOH2 plus and A minus as the resultant ions. Now, what happens is when we add different acids, they ionize to different extent. For example, I am going to take some acids. These are all highly strong acid, that is HClO4, hypochloric acid, HBr, sulfuric acid, H2SO4, HCl and HNO3. Now, when these acids are added to acetic acid, since acetic acid is a weak acid, these acid has to compete with acetic acid for donating the proton. So, there is some difficulty in donating a proton, and therefore, there the acids are differentiated, and we have the strongest acid as HClO4 being the strongest one, then comes HBr, then comes sulfuric acid and then the HCl, and last is HNO3. So, using this you can differentiate which is a stronger acid and which is a weaker acid on comparison, and therefore, acetic acid can be considered as a differentiating solvent. This cannot be found out when we use water because all appear to be strong acids. Okay. Now, there is a general term we can use for that. For acids, if I am taking an acid and if I have to find out whether we will have a leveling solvent or a differentiating solvent, depends upon, if for an acid, if I am using a solvent which is a strong base, they will be acting as leveling solvents. If I am using a weak base for acid, then there will be they are differentiating solvents. For bases, if I use strong acids, that will be leveled, they will be leveling solvents, and if for weak acids are used, you have them as a differentiating solvents. Okay. Now, let us conclude. We have been seeing in this session, that is relative strength of acids and bases and factors that influence the relative strength of acids and bases. First one was the influence of the solvent, and in solvents we have the effect of proton accepting and donating nature of the solvent, then nature of polarity of the solvent and dielectric constant of the solvent. Then depending on the substituents, we have electron withdrawing substituents and electron donating substituents. Then comes the steric effect, then p-pi back bonding, then factors such as electronegativity, charge density and hydration energy which determines their strength, then resonance effect. After that, we were discussing about the leveling effect and differentiating effects of solvents, and for acids we have told that if we use strong bases, they become leveling solvents. If we are using weak bases, they will be differentiating solvents, and for bases, if I use strong acids, that will be leveled, and if I use weak acid, they can act as differentiating solvents. Thank you.